So binomial series. So a little, first of all, a little algebra review quickly. And I'm going over this just to sort of orient you into, where this comes from or how this relates to the algebraic binomial series you've seen before. So I know you remember from Calc 1 us looking at Pascal's triangle and how to use that to expand powers of binomials. So for example, you remember that Pascal's triangle is this guy. And I'm sure you don't remember all the detail here, but I'll remind you that the numbers in these rows correspond to combinations. And by combinations I mean when I say 3 choose 1, which I write as 3 over 1 with no fraction bar inside parentheses. And if you have seen this in high school before, you may have seen it like this. 3 with a big C and then a 1 with the 3 and the 1 subscripted. And what this means is if you have 3 total objects and you choose one of those objects, this is the number of ways to select one object from a group of 3. And of course, if I have 3 objects, 3 marbles, and I reach into a bag of 3 marbles and I pick one of them, there are 3 possible outcomes. You either get marble 1 or marble number 1, marble number 2, marble number 3. What's 3 choose 2? If your marbles were in the bag and they were numbered 1, 2, 3, if I asked you to reach into that bag and take 2 of them, well, there are 3 ways that could happen. You'd either take 1 and 2, or you'd take 1 and 3, or you'd take 2 and 3. There's 3 possibilities, 3 combinations. Okay, what's 3 choose 3? That's kind of a silly one. That's reach into the bag of 3 things. How many ways to take out all 3 things? 1 way. You just reach in and take all 3. Okay, here's the really odd one. 3 choose 0. How many ways, and I'll ask you guys this, how many ways to reach into a bag of 3 things and choose none of them? It's kind of a trick question.
I guess 1.
Yeah, there's 1 way to do it. You reach in and you don't take any. There's 1 way for that to happen. Okay, notice that these numbers, of course, the 1, 3, 3, 1, are these numbers right here in Pascal's triangle. And so the interpretation, and we're not proving why the numbers in this triangle stack up the way they do to give these combination numbers, that's another class totally, but we'll just say this number means 3 choose 0. This number means 3 choose 1. This is 3 choose 2. This is 3 choose 3. Actually, because of the symmetry of the numbers, you can see that I could call this one 3 choose 0, and this one 3 choose 1, and 3 choose 2, and 3 choose 3. Okay, that means there will be a similar interpretation for every other row. In that blue row, the 1 would be 4 choose 0, the 4 would be 4 choose 1, the 6 would be 4 choose 2, the 4 there would be 4 choose 3, and that 1 would be 4 choose 4. Okay, so I know several of you have seen that before. If you haven't, don't worry too much about it. This is a bit of background. For what we're going to do with this, we're not really going to need Pascal's triangle. Only to this extent. If you remember what we came up with in Calc 1, or if you've seen this in an algebra class before, is that when you expand a binomial to a positive integer power, so n is, say, 1 or 2 or 3 or any other positive integer, what you get is a certain number of x to the n's, a certain number of, let me leave myself a little more space there, a certain number of x to the n minus 1 y's, a certain number of x to the n minus 2 y squareds, all the way up to a certain number of x, y, n to the n minus 1's, plus a certain number of y to the n's. Okay, it turns out that the mystery coefficients that show up in this expansion of this binomial, so all these missing coefficients where I'm leaving the blanks, those are the numbers from that Pascal's triangle. Okay, so which row am I talking about? Well, this is the row for 3 choose something. This is the row for 4 choose something. This is the row for 5 choose something. So if I had n things, this would be n choose 0. This would be n choose 1. This would be n choose 2. All the way up to the very last one. And by the way, I should have left a blank there for that coefficient. Well, the very last one would be a 1, which is n choose n, and the one before it would be n choose n minus 1. And those numbers in yellow are the numbers from that row in Pascal's triangle. That is, if n was 4, it would be the row that had the 1, 4, 6, 4, 1. If n was 5, it would be the next row. Okay, so for example, if I had x plus y to the 4th, what I'm saying is there would be 1 of something plus 4 of something plus 6 of something plus 4 of something plus 1 of something, where the 1, 4, 6, 4, 1 are the numbers from that row that starts out with 1, 4 in Pascal's triangle. And what I'm saying is, well, think about what would happen if you multiplied that out. When you do x plus y to the 4th, that is, if you do 4 of those, obviously the first thing you're going to get is x times x times x times x, and there's going to be 1 of those. What Pascal's triangle, or this binomial theorem we're going to call it, says is that you would then have 4 of x cubed y. You would then have 6 of x squared y squared. You would then have 4 of xy cubed. Then you would have 1 of y times y times y times y, which is y to the 4th. Does everybody see the pattern on what's happening to the x's and the y's? You're starting out with 4 of those, then there's 3 of them, then there's 2 of them, then there's 1 of them, then there's none of them. In this first term you had no y's, but then you had 1 y, then you had 2 y's, then you had 3 y's, then you had 4 y's. Notice the total number of factors in each term is 4. 4 x's in the first one, 3 x's, 1 y in the next one, 2 x's, 2 y's in the next one. Alright, now, all of that's just a little algebra review and not totally essential for what we're talking about now, but it does at least get us to the point where we can say x plus y to the n is definitely a summation. It is k equals 0 to n choose k, because in that sum, k is going to go from 0 to 1 to 2 to 3 up to n, which is what those bottom values are doing. The number in the top is n, which is why I'm using a fixed n there. And then what goes inside is what? Well, you start out with x to the n, and then it goes x to the n minus 1, x to the n minus 2. So the correct form there would be x to the n minus k. That way when k is 0, you have x to the n. When k is 1, you have x to the n minus 1, and so on. What would go here for y? Well, you have no y's here, which means y to the 0. You have y to the first here, You have y squared here. I think I just want y to the k. And so if I write out several terms from that summation, what I'm going to see are these terms I've listed up here from that use of Pascal's triangle. And this is definitely true in algebra for n greater than or equal to 1, n an integer. And taken all together, this is, if you've seen it in, say, high school pre-calculus, this is what they call the binomial theorem. And again, the way we used it in Calc 1 was just to, as an aid to expand some of these things when we were doing some derivative stuff early in that class. Alright, now, that's a bit of background. Now we're at the point where we actually get to something we're doing here. So, notice in this function, if I did 1 plus x to the m, that looks like a binomial. It looks like I've made this x here a 1, or how about just I moved that x here and I made that y a 1, and I've just called this m, or this n an m now. Okay, that's just customary. The reason for the change from n to m is because in the binomial theorem, that n has to be a positive integer. With what we're going to do next, this m right here does not have to be an integer. It could be a fraction, for example. Alright, so what we're going to look at is 1 plus x to the m, where x is any real value, and m is, ideally, it could be any number, any real number. Alright, let's say I called that y, or let's say I called that f of x. Okay, now that's as good a function as any for using the Taylor series formula on to try and generate a Taylor series from that function. In fact, let's do the Maclaurin series for this. And this will be some good practice for generating Maclaurin. So Maclaurin series for this function. So you know how that goes. I need the function. I need some derivatives. And this process, if you've looked at a few of these and you've seen me doing them in the notes now, it looks like the process is always to take a few derivatives, and if you're lucky, there's a nice pattern to those derivatives. Now, I will say in general there are definitely weird power series where the Taylor coefficients do not have a nice pattern to them. Fortunately, most of the ones we use a lot really do have nice patterns. And those are those patterns you see in those formulas on page 696. Okay, this one also has a nice pattern, a super nice one. What's the next derivative? Well, you just pull the m minus 1 down, and of course you subtract 1 from the power. And if I took the third derivative, it would be the same thing, except I would pull down the m minus 2. And now this would be m minus 3. In general, if I took the, let's say, nth derivative, well, let's be careful here. This was the first derivative. This was the second derivative. This was the third derivative. Now, the important part I want to look at is this part. Do you see a pattern that I could write down there for the nth derivative in general? It would have to start out with m, and then it looks like each one of those expressions I've highlighted in blue starts out with m times m minus 1, and then it's a product of successively smaller values where I keep subtracting 1 over and over again until I get down to what? Well, let's look at this one in particular, just to pick one. do we agree that m times m minus 1 is the same thing as m times m minus 1 down 2? And if I was trying to write what the last one was, would it be m minus 2 plus 1? Notice that that is m minus 1. Okay, so what that means is, if I tried that pattern on this one, okay, is that the same thing as m times m minus 1 down to m minus 3 plus 1, which would be m minus 2? And the answer is yes. Okay, notice the number I'm plugging in here is n. So what I'm driving at is, when I take the nth derivative, what should this part in blue be? It should be m times m minus 1 times m minus 2 down to, what would the very last factor be? Can somebody tell me what that last one would be?
M minus n plus 1.
That's the one. I'll do it in the same color. And we've actually run into this somewhere else. Last week when we were doing something, we ran into the same kind of expression. Alright, now, question. If we're doing the Maclaurin series, so for Maclaurin, our center is 0, right? So we know how the Taylor coefficients work. I get each one of those Taylor coefficients by taking the nth derivative at the center divided by n factorial, and then of course I multiply that times x to the n to get the Maclaurin series. Okay, so in this case, what is each one of these parts when I plug in 0? Isn't every one of those just 1? Which means this is 1, this is 1, this is 1, this is 1. And what that means is, my first derivative at 0 is m. That's coming from here. My second derivative at 0 is m times m minus 1. And in general, my nth derivative at 0 is m times m minus 1 down to m minus n plus 1. Now, of course, that means the Taylor coefficients would be that expression we've just cooked up down here divided by n factorial. Now, by the way, don't forget, when you write out the Taylor series in general for a function, the Taylor series for any function is supposed to be what? N equals 0 to infinity, nth derivative at the center, which in the case of Maclaurin is 0, over n factorial x to the n. Okay, so what is that? Well, the very first one, when n is 0, of course that's 1 and that's 1. And by the way, just to clarify this, notice that when I say n equals 0, when I write f0, the 0th derivative is just the original function. So a Taylor series always starts out with f of the center for Maclaurin, which in this case would be f of 0. And then what do the rest look like? They look like f prime of 0 over 1 factorial x, f double prime of 0 over 2 factorial x squared, and so on. Okay, putting all that together, what is the Maclaurin series for 1 plus x to the m? Well, it's this guy right here, where f of 0 is what? It'd be 1 to the 0, if I just plug 0 into that, which is 1. Okay, what's f prime of 0? We said that was m. m over 1 factorial times x, that'd be mx. What's the second derivative? Well, we said that was, wherever I wrote it, m times m minus 1. So that would be m times m minus 1 over 2 factorial x squared. What's the next one? It's m times m minus 1 times m minus 2 over 3 factorial x cubed. Plus dot dot dot, what does the general nth term look like? It looks like m times m minus 1 times m minus 2 dot 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 down to m minus n plus 1 over n factorial x to the n plus dot dot dot, because this is an infinite Taylor series. So this guy is the Maclaurin series for, let's say, Maclaurin for 1 plus x to the m. Notice that formula is valid even if m is a fraction. So this is really a binomial expansion, an infinite one, but it does not rely on m being a positive integer. M could be 1/2, m could be 1/3, and this derivation is still valid. Alright, now, we have a big question here, and this goes back to the stuff we've been talking about for the last couple of days. We just started with a function. We generated, let's say, the Taylor series, in this case the Maclaurin series. Okay, what was the big theoretical question from yesterday? Does the Maclaurin series or Taylor series and the function itself have to be exactly the same? Do they have to equal the same value? And the answer is no. We saw that the only way we're sure, let's say we know that 1 plus x to the m actually equals its Taylor series, which, by the way, the Taylor series could be written as 1 plus n equals 1 to infinity m minus 1 down to m minus n plus 1 over n factorial x to the n. I know these two are actually equal if what? The limit as n goes to infinity of the Taylor remainder is 0. And that's the thing we talked about yesterday. Okay, now, what's the other thing I said yesterday that other than doing error estimation, like that very last example I did yesterday, the rest of what we talked about yesterday is more or less for theoretical interest. It gives me a theorem that can give me a condition under which I know a function is actually represented by its Taylor series. Alright, so to be sure that this function really does converge, or the power series really does converge to 1 plus x to the m, I could try to prove this, but I will say that that is pretty hard. It is doable, but it's very intricate and you run into some hairy stuff there. So we're not going to do that. We're going to go at it a little bit different way. And then once we've got it, we've got a new formula that we can use. So, in fact, let's do this backward, and I just decided on the spot that we'll do this backward. We'll look at the proof here near the end, because the important part is for you to see a few examples of this thing in use. So before I go to the examples, let's just say one more thing. And I'm going to leave this for you to do, and you should definitely try this later. If you apply the ratio test to this power series, that is this one that we're talking about here, you will find an interval of convergence, absolute value of x less than 1. In other words, open interval -1 to 1. So this binomial series, which is what we're calling this, converges on the open interval -1 to 1. And you can get that quite easily by just doing the ratio test, similar to what we did a few sections back, where we took this guy, we said let's take the limit as n goes to infinity of all of that, if we call that all a sub n plus 1 over a sub n, figure out what that limit is, and you want that limit to be less than 1. And of course when you do that, there will be an absolute value of x that comes out times something. And I'll just say you should verify this for yourself. The limit of that something right there is 1, which means the interval convergence is -1 to 1. You would also want to check the endpoints, and it turns out it diverges at those two endpoints. Alright, so let's take that for granted, although it's not too hard to show. And so what we have now is, assuming this is all correct, the binomial expression 1 plus x to the m has a Maclaurin series of 1 plus n equals 1 to infinity m minus 1 down to m minus n plus 1 over n factorial x to the n, and this converges on -1 to 1. Okay, let's stop there. Is everybody okay so far with what my formula says? Let's look at an example to see if you got it. Okay, if I wanted to look at a very weird function, and this will give you an idea of why this theorem is pretty useful. Let's say I wanted to look at 1 over the square root of 1 plus x. Okay, and of course the first thing I notice is that's 1 plus x to the -1/2. This is definitely binomial with m equals -1/2. Okay, which means on my interval of convergence, my formula says that 1 plus x to the -1/2 should be 1 plus infinite series n equals 1 to infinity. Okay, now let's look at our formula here. M is -1/2, so this should be -1/2 times -1/2 minus 1, which would be -3/2. The next one after that would be m minus 2, which would be -1/2 minus 2. That would be -5/2. Okay, down to the very last one, which would be -1/2 minus n minus 1. All of that over n factorial x to the n. So far, so good? And that's just using this formula straight up. And the only thing I've done is just substituted -1/2 for m. Alright, question. Somebody can tell me this. In this general expression right here that we've written, how many factors are there? How many factors are sitting there? If you say m times m minus 1 down to m minus n plus 1. How many numbers are there? If you go from 0 to 1 to 2,
N.
yeah, there's exactly n factors there. which is not a big surprise. It would seem like if I got that from taking derivatives, and taking a derivative with the power rule just continuously pulls down exponents, then it seems like after n derivatives I should have n factors there. Okay, so there are exactly n factors there. Okay, meaning when I look at our little example here, it should be clear that there are n factors here. There are n of them, right? And if I wrote out what I have there, so let me write this out, negative 1/2, and I'm going to go through this example in this detail because most other binomial series have this same kind of behavior. So if you have this example to look at, this will kind of show you where the author or myself might be coming up with this way of writing this. So I have that, dot, 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 down to negative 1/2 minus n, and that should be a plus 1, shouldn't it? That's what Pat said before. It was m minus n plus 1, so that red plus, that should be a plus. Okay, so let's just look at that part. We just said there are n factors there, right? So that means I should be able to pull out negative 1 to the n, and that would leave a positive 1/2 and a positive 3/2 and a positive 5/2 all the way down to, well, same thing on this last one. I've pulled out a negative 1, which means I should have 1/2 plus n minus 1. Which, of course, what is this actually? It's n minus 1/2, or if you want to call it negative 1/2 plus n. So far, so good. So if it's okay, I'm going to just call this part n minus 1/2, because that's what it is. So far, so good. What's another way I could write n minus 1/2? Well, since I see all these other guys have denominators of 2, how about I just call this 2n minus 1 over 2? Just to combine these two and get a fraction that has the same denominator as all of these. In which case this guy now becomes 2n minus 1 over 2. Everybody with me there? Okay, now, what I see then when I multiply out all n of these fractions, because there are n fractions there now, what we get is what? Negative 1 to the n. In the bottom, aren't we going to just be multiplying a bunch of 2's? In fact, there will be n of them, so that bottom should be 2 to the n. Okay, what's the rest of it going to be? The rest of it's going to be the product of all these. Does everybody see that all of those numerators are all odd numbers? You started out with a 1, and of course you were subtracting 1 from each one of these fractions, and when you do that, what you're going to get are the odd multiples of 1/2. So in other words, when I multiply all of those, I'm going to get 1 times 3 times 5 all the way down to, notice this last one even is odd, the way I have it written now. 2n minus 1 is an odd number. And that is the last factor. Notice there are n negative 1's, there are n 2's, and in this green product there are even n factors there. There's n of everything. So when I put that all together, what I have then is 1 plus x to the negative 1/2 is 1 plus series n equals 1 to infinity. And what I'm doing now is just writing this in a better way, a nicer way. It looks like it should be negative 1 to the n times 1 times 3 times 5 down to 2n minus 1 over 2 to the n. Don't forget the n factorial. And don't forget the x to the n. And there is our binomial series for 1 plus x to the negative 1/2. And I've just walked you through the simplification that's normally done on this form of the series. Since you get a bunch of these fractions that are all very similar, oftentimes you're going to have the same denominator in the bottom of all of them. If you start out with a 1/2 or a negative 1/2 and you start subtracting 1 over and over again, you're going to get a bunch of halves. If this guy to begin with had been a third, if you start subtracting 1 from a third, you're going to get a bunch of different kinds of thirds. There will always be a number in the bottom of each one of those fractions that's the same number for every single fraction. Alright, now, this would answer the simple question of what is the closed form for the Maclaurin series for 1 plus x to the negative 1/2, which was our 1 over square root 1 plus x. This power series converges to that function on that interval of convergence. Okay, which means what? If I wanted to evaluate this function at any number between negative 1 and 1, we're saying that this power series would converge to that value, meaning if I use enough terms in this series, I know I can get as good an approximation of 1 over the square root of 1 plus x as I want. How far would I need to go if I needed a certain accuracy? That's where I would have to use that Taylor's remainder theorem. And I will do one of those for you here in a minute, so you've got another one of those to look at, similar to the one we did yesterday. Okay, so I've got, let's see, do I have time? I think we're going to skip the proof. I know you guys probably don't mind that. He doesn't really do it in the book. That is the proof of, or settling this question, does the power series generated by the function converge to the function? Are you all willing to take my word for that? Or will you insist on me doing the proof? I am fully prepared to do the proof, but I'm not sure.
We're okay.
Yeah, I think we can skip that for this one. It's a bunch of algebra. There's nothing very profound there anywhere. It's mostly an exercise in manipulating series. And there's some good stuff in there, but we can skip it for now. Okay, so let's actually, for another example, let's look at this one that we just cooked up, which was this guy. And we said it was what? 1 plus, and I'll just copy down what we had. It was what? Negative 1 to the n, 1 and 3 and 5 down to 2n minus 1 over 2 to the n factorial x to the n. I think that's right. Yes, that's right. Okay. Now, here's where we can pull in some other things that we've done before. What do we know once we have a power series for a function? This is where we can go back to the things we did early on in 8.8, where we said if we knew a power series for a function, we could get other power series by taking derivatives, by integrating, by plugging in kx or x to the k inside the power series. And of course, that's part of what you're doing in some of this online homework, is getting series from other series by using things you know like that, including geometric series techniques. Okay, what I want to do here is, and by the way, the one we just did was a plus, wasn't it? My sign is wrong there. We just did the 1 plus. So here's what I want to do. Let's just replace x by negative x squared, which that's allowable, right? If f of x is 1 over the square root of 1 plus x, what we're talking about doing is just evaluating that function at negative x squared. Okay, notice what I'm doing there. I'm replacing x by a constant multiple of a constant power of x. That's combining those two little tricks that we've got. We know that if we have a power series for a function, we can replace x by kx and get the power series for that function. We can replace x by x to the k and get a power series for that function. I am combining those two by using a multiple of negative 1 and a power of 2. Okay, why am I doing that? Because it leads to this function, and that function should jump out at you. What is that function? Why is that one important? What is so great about that function? That is 1 over...
Is that inverse time?
Yes. Everybody agree with that? Antiderivative of him is definitely sine inverse, or to put it another way, derivative of sine inverse is this guy. Okay, so we're coming at, or we're getting to, the power series for sine inverse. And if you think about what we've got so far, we're accumulating quite a few that you already know and can use. We've got power series for sine and cosine, for e to the x, for ln of 1 plus x, for tan inverse. Now we're going to see how can I get power series for sine inverse. Well, it's going to come from binomial. Okay, so, quick question. When I say replace x by negative x squared, what do I mean? I mean replace that x by negative x squared. So if I do that, I should have 1 over the square root of 1 minus x squared is equal to 1 plus series n equals 1 to infinity, negative 1 to the n, all the rest of that stuff. So 1 times 3 down to 2n minus 1 over 2 to the n factorial. And now this part just becomes negative x squared to the n. And notice what that part is, and that's an n out there, not a 2. Notice what this part is. It's really just negative 1 to the n x to the 2n. Everybody good with that? Which means I'll just relabel this as negative 1 to the n x to the 2n. Question, what do you get when you put this together with this? You get negative 1 to the what? If you multiply those together, yeah, which is 1. Okay, good. Since that power is even now for all n, these two together just, if you want to call it, cancel each other out and just make a positive 1. So what we're saying now is we have a simple series for 1 over the square root of 1 minus x squared. It's 1 plus n equals 1 to infinity. It's just the 1 times 3 times 5 down to 2n minus 1 over 2 to the n factorial times x to the 2n. What am I going to do next? I'm going to integrate both sides with respect to x. Okay, if I integrate the left side with respect to x, then of course I get sine inverse of x. If I integrate the right side, then of course this first one, don't forget about him, he just becomes an x, plus, well, to integrate that power series, let's just integrate term by term. And of course the only part that actually gets touched is the x part. This part right here just carries down. That means when I integrate, I'm going to have 1 times 3 times 5 up through 2n minus 1 over 2 to the n factorial, x to the 2n plus 1 over 2n plus 1 plus c. Don't forget the plus c. With me so far? Take a second and look at that, make sure it makes sense. And just notice the only thing I did when I went from this line to this line is I just integrated with respect to x, which means this coefficient, which is constant as far as x is concerned, just becomes part of the antiderivative. Which is why the only thing that changed when I went from that line to the next is this part right here. Alright, now, question, what is the typical trick that we've seen many times for figuring out the c? What is the usual trick? And you will have to do this once, maybe twice somewhere in that online homework. That is, you'll need to integrate a power series. There will be a plus c, and you'll need to figure out what the c is. Now, in most of the series we encounter, in fact almost all of the ones that, the standard ones in that list on page 696, any of the ones that you get by doing integration like this, the c is almost always 0, but it doesn't have to be. And I'm pretty sure there's one in your homework where the c is not 0. But what is the trick for determining the c? Don't you pick an x value of some kind? And usually x equals 0 is the one that works out real well. So in this one, notice, if I plug 0 into this equation, I have sine inverse of 0 equals 0 plus, okay, notice in this series, that is all of this, what do you get when you plug in x equals 0? My first term is an x cubed term. When n is 2, this is an x to the 5th term. When n is 3, this is an x to the 7th term. If your terms in this series are something x cubed plus something x fifth plus something x seventh and so on, and you plug 0 in for x, what is this entire series going to evaluate to?
Just 0.
Yeah, the whole thing's just 0. Plus c. In other words, what's c? It's sine inverse of 0. And what's sine inverse of 0? It's just 0. Okay, big surprise, the c is 0. Meaning, we have a working power series now for sine inverse. And make sure you have this one written down in case you need it. I'm not sure if it's needed in your online homework or not, but I don't think it's in your table on page 696. It may be, but I don't think so. And the only thing I did there is I just moved the 2n plus 1 over into the denominator here and put those together. So in case you need it, there is the power series for sine inverse. But it shows you a good application, a roundabout one of binomial series. And if you think about it, think about what we've done so far. How did we find tan inverse series? We integrated 1 over 1 plus x squared. Okay, we could do that because that was geometric. Okay, the thing we couldn't get around before was how to find sine inverse, because it was the antiderivative of a fractional power of 1 plus negative x squared, and that is binomial. So that's how binomial gets us the power series for sine inverse. Alright, we've got time for one last example. And this can be another one that can also kill two birds. We can look at that Taylor remainder idea again from yesterday. So I want to compute the cube root of 25 accurately to 3 decimal places using the binomial series for 1 plus x to the 1/3. And this is a very good example to close on because it gives us another binomial example, and it will walk you through this Taylor remainder idea one more time. Alright, first of all, let's just write out what 1 plus x to the 1/3 is. According to our formula, it should be 1 plus series n equals 1 to infinity. Okay, how does it go? It's supposed to be m times m minus 1 down to m minus n plus 1, except our m is now 1/3. So this should be 1/3 times 1/3 minus 1. In fact, I'll write that out. The next one would be what? That minus 1. So actually, let's just go ahead and calculate these. If that next one is supposed to be m minus 1 and this one's 1/3, what's the next one?
Negative 2/3.
Good. Okay, let's do another one just for another. So it means whatever you have here, subtract again. That is subtract 1 again, which would give you
Negative 5/3.
Yep. Let's do one more. Let's do one last one.
Negative 8/3.
Good. Okay, and obviously there's a nice regularity to these. Once you figure out what that denominator is, it's easy to just crank out as many of these as you need. So what we're saying in general here is what? This should look like 1/3 times negative 2/3 down to the usual 1/3 minus n plus 1 over n factorial x to the n. There's our general Maclaurin series formula. I'm just writing it down. Basically, I haven't done anything other than just put 1/3 in where the m is. Okay, but by doing a little scratch work down here, I can see now that 1 plus x to the 1/3 is actually what? It's 1 plus, okay, the first term would be what? 1/3 x? Does everybody see that? When n is 1, you're only going to capture this first one, and this would be 1 factorial, and this would be x to the first. Okay, now when you go to n equals 2, then you're going to be on the x squared term. This down here is now 2 factorial. And now since the second degree term comes from taking a second derivative, there should be 2 factors in that. So what is the next term in this power series for this function? It's 1/3 times negative 2/3, which would be negative 2/9 times 1 over 2 factorial times x squared. Everybody with me there? So far, so good. What's the next one? Well, it would be the 1/3 and the negative 2/3 and the negative 5/3. Notice when I multiply all those, it's going to be positive now, and it would be what, 10 over 27? It would be 10 over 27, but don't forget, you are doing a Taylor series, so you still need that n factorial on the bottom. And we're on the third degree term, so there'd be a 3 factorial now. Okay, what would the next one be if we did one more? So we said what? It was 1/3 and negative 2/3 and negative 5/3 and negative 8/3. I think we're back to a negative now, and we're up to 80 over 81, and it would be minus 80 over 81 times 1 over 4 factorial x to the 4th, etc. With me so far? I'm just, this would be like if this is one of your questions in the online homework where they were asking for, let's say, the first 1, 2, 3, 4, the first 5 non-zero terms of the power series, the Maclaurin series for 1 plus x to the 1/3. These would be your first 5 terms. And actually, what's the other way they could ask it? This is similar to that one you asked about, Patrick. They could ask me, what are the Taylor coefficients for the first few terms of this Maclaurin series? And of course, you'd say C0 is 1, you'd say C1 is 1/3, you'd say C2 is minus 2/9 times 1 over 2 factorial, and that's actually just minus 1/9. And similarly, you could simplify these. I'm sure every one of those is going to break down a lot. But is everybody okay with how I'm getting those numbers? That's the important part. Okay, now, what does all this have to do with approximating the cube root of 25? And this is just an example to show you how I can get things like this. Okay, if you think back to Calc 1, this relates to something we did back in Calc 1. Back in Calc 1, we did problems where I would ask you things like, let's approximate the square root of 102 using the tangent line, or I would say, let's calculate the square root of 97. Okay, and we're not going to go back through these kind of problems right now, but when we were doing those, part of what you tried to do was to find the closest number to 102 at which this square root function was nice, and of course that's obviously 100. And it's the same thing for this one. What's the nicest close number, or the closest nice number to 97 that has a nice square root? Well, it's still 100. Alright, that's what I want to try and do here. So when I'm looking at 1 plus x to the 1/3, if I'm going to try and approximate the cube root of 25, which would be 25 to the 1/3, well, there's a couple of ways I could do it. Obviously, the most basic way is I could call that 24. There's not much motivation for where that would go from there. Here's another way I could do it. I could say the cube root of 25 is the cube root of 27 times 25 over 27. Okay, notice if I write it that way, I can take the cube root of 27 and pull it outside. And when I do that, what's left inside is 25 over 27. Notice that that is 3 times the cube root of 1 minus 2 over 27. And now you should be seeing why I went this direction. When I'm doing the binomial series, it's not like what we did in Calc 1, where I'm just asking you to make 102 close to something that has a nice square root. I actually need to pick something that's close to 1 to make this binomial work, because it's 1 plus x. Well, by using this little multiply and divide by the same number trick, and of course I have picked a number that is the closest nice number to 25, well, he comes outside, and what's left, hopefully, is something that will be pretty close to 1. And with the numbers I've cooked up, it is. It's fairly close. It's within 2/27. Okay, so if I ignore the 3 for just a minute, so let's ignore the 3 and just look at cube root of 1 minus 2 over 27, which is 1 plus a negative 2 over 27 to the 1/3. That is definitely binomial. It's binomial m equals 1/3, and x is actually negative 2/27. Now, if you would have had trouble coming up with this approach, I understand that, but now that you've seen it, this gives you an example of how you could approximate something like this. That is, in general, this is how I could try to approximate cube roots or square roots or fourth roots or anything else of a number. I could do what I'm doing in this example. Alright, so let's write out then what we've got. If I just work on this, and I'll ignore the 3 for right now. If I just work on him, I know 1 plus a negative 2/27 to the 1/3. Well, according to my binomial theorem, let's just put an x there for a minute. It should be what? 1 plus n equals 1 to infinity. And then we just write out the binomial formula, which would be 1/3 times 1/3 minus 1 down to 1/3 minus n plus 1 over n factorial x to the n. And of course, what am I ultimately going to do? I'm going to plug in x equals negative 2/27. And when I plug that value in here, I know that this Maclaurin series will converge to the value I want. And then I'll just need to multiply it by 3. Now the question is, how many terms do I need to use to make sure I've got the accuracy I want? Okay, so very quickly, and I am over time now, but if you don't mind, let's just write this down quickly, and then you can look at this later. Look at R2 of negative 2/27. Now, let me remind you, what does that mean? This is the Taylor remainder if we stop at the second degree Taylor polynomial. And if you go back and look in your notes, you'll see that's exactly what R2 is. In other words, the Taylor series can be written as everything up to the second degree term plus the Taylor remainder, which is the tail of the infinite series. Now, what did we come up with yesterday? We said that when you want to look at that Taylor remainder, it's the n plus first, the next derivative of the function at some number over n plus 1 factorial x to the n plus 1, where, and this is the important part, c is between your center and your x value. Well, in this case, the x value is negative 2/27, and the center is 0. So what I can say then is R2 of x, and it's actually going to be R2 of negative 2/27, is the third derivative, because notice if it's n, I want to look at the next derivative. So it'd be the third derivative at some number c over 3 factorial times x, which is negative 2/27 cubed, where c is between what? Well, the center, which is 0, and the x value, which is negative 2/27. In other words, where is c? It's in between negative 2/27 and 0. So far, so good? Okay, by the way, what is the third derivative? If the function is 1 plus x to the 1/3, let's just do this again. It's the same way that we got the coefficients in the power series. This would be 1/3 times 1 plus x to the negative 2/3. This next one would be 1/3. This would be second derivative. 1/3 times negative 2/3 times 1 plus x to the negative 5/3. Third derivative, which is the one I want, is 1/3 times negative 2/3 times negative 5/3 times 1 plus x to the negative 8/3. So far, so good? And it seems like I might be off by... Well, no, not actually, I'm not. It's just the way I wrote this. So I kind of jumped ahead a step, which is okay. But I'll just point out that guy right there. Looks like 1 plus x to the 1/3 over 1 plus x cubed. That's the same thing. And so, of course, what are we trying to estimate? We're trying to estimate how big f prime of c is. And where is c? It's a number that's in there. So question for you all, is it doable for you all to get an upper bound on this interval? Is that doable? What is this function really? It's 1 over 1 plus x to the 8/3. I think you could easily figure out if that's an increasing or decreasing function. And then you could say, where is the absolute value of this the largest? And if it's similar to the problem we did yesterday, it's going to be at one of these two endpoints. So I'm going to leave that part for you to do. I'll just say that on this interval, that's a Calc 1 problem. You should be able to tell me where this guy has its maximum, or in other words, can you tell me some upper bound for 1 plus x to the negative 8/3 on the interval negative 2/27 to 0. Once you find that, will you have an upper bound on f prime of c? The answer is yes, because it will be whatever this is times whatever this is. And I actually didn't work out the last part here, so I'm going to leave this for you guys. Once you figure out what that max is, multiply all of this together, and you will have a maximum for this. Everything else is already a fixed number, which means at that point, what will you have? You will have an upper bound on the size of that remainder, the one that you get if you stop at the second degree term. And I will just tell you, I don't have it written down here, but I did the calculations. When I calculated this based on the upper bound that I found for this thing in yellow down here, I came up with that remainder being less than 0.00006. And I don't know where my notes went, but I had this all worked out. But I wrote down the 0.00006. Okay, by the way, what were we trying to figure out here? If we could compute this accurately to within 3 decimal places. if my error is less than this, haven't I computed it to within 3 decimal places accurately? The answer is yes. Now, what this means is, and I sort of jumped to the end here, I also checked R1. That is, what would the error be if I stopped at the first degree term, and it was not small enough to guarantee that I was accurate to 3 decimal places. So the part that's missing here in the example I'm showing you is first I checked this for R1, and when I did that I could not convince myself that R1 was less than, well, let's see, if we want it to be accurate to 3 decimal places, don't we want Rn of negative 2/27 to be less than 0.0005? If you remember what we did yesterday. Accuracy to 3 decimal places means you'd have to be zeros in your first 3 places, and that 4th decimal place would have to be less than 5. Well, when I did this one for R1, I didn't get this to be less than 0.0005. When I went to R2, though, I got it to be less than 0.00006. Okay, now, let's just wrap this up, because I actually have to get to class in 5 minutes. What is the final upshot here? I would use the first 3 terms of the binomial series to approximate this. I would use the first degree term, the constant term, the first degree term, and the second degree term. And that's why I'm saying 3 terms. Notice I was able to show that R2 was less than the error I'm after. R2 is the error if you stop at the second degree Taylor polynomial. Okay, so that means when you write out your series on the previous page, that means I would be using up through those terms right there. So I'll leave this for you to finish, but what I'm saying is, how would you approximate now with this accuracy 1 minus 2 over 27 to the 1/3? You would simply plug in negative 2/27 for x. And you're using just the second degree Taylor polynomial. I know my accuracy will be as good as I want it because of what I showed on the next page. Now don't forget, what's the one thing I've left out here? There was a 3 in front of this, so I would have to put a 3 in front of this. That 3 will not affect the number of terms necessary to get the accuracy you want. In fact, I could have included that 3 in my function down here. I just left it out because it was easier just to look at this part. That's just a constant multiple in front. That won't affect the number of terms needed to get this accuracy. So, upshot here is, you may run into a few questions where they ask you to approximate something like a cube root of a number. If you go back and look at this example, and I think there's also one in the book, this is the way you can do it for something like cube root of 25, or 4th root of 14, or 5th root of 34. Those are all roots that are close to something that has a nice root of that type.